Hello, welcome to a video on 2014 FRQ number 4, where we have train A runs back and forth on an east-west section of a railroad track. Train A's velocity, measured in meters per minute, is given by the differentiable function VA of t, where time t is measured in minutes. Selected values for VA of t are given in the table above. So for our first section of this problem, it asks us to find the average acceleration of train A over the interval 2 to 8. In other words, acceleration means the slope of this velocity function, or the rate of change. And when it asks for the average acceleration, you basically use the slope formula for these 2 points, since it's asking the value from 2 to 8. So for A, we got right here, take the y value, negative 120 minus 100 over 8 minus 2. That would give us negative 220 over 6, which simplifies to negative 110 over 3 meters per minute squared. Remember to add the squared to represent the acceleration value, and for this section of the problem, it's an all or nothing. So basically you have to get this value right to get full points. If you get any part of this wrong, it's no points for this section. So for question B, it asks us one of those conceptual questions in which it wants us to decide whether the conclusion that train A's velocity is negative 100 meters per minute between 5 and 8 is true, and give a reason for your answer. So for this problem, we always try to prove it as true first, and if it doesn't work, then it must be false. So from our original setting problem, we notice that, as here it's underlined already, that this VA of t function is a differentiable one. In other words, that means it is also a continuous. And with these y values for 5 and 8 right here, we can prove that VA of 8 is negative 120, is less than negative 100, and also negative 100 is less than 40, which is VA of 5 right here, this y value for here, and that must be true. This statement must be true if it's continuous. And as a visual person, I'd like to understand it like this graph right here. So if we have 5, 40 and 8, negative 120, and it's continuous, at some point it would reach this y value of negative 100. So this statement must be true. And with that, basically proves right that the train did cross this negative 100 mark between these two intervals. And with a certain theorem called the intermediate value theorem, or in other words IVT, which exactly explains this concept, we explained that there is a time t between 5 and 8 in such that VA of t is negative 100. So that's your conclusion, 1 point, and this equation is 1 point. Okay, so for part C of this problem, it asks us to find train A position at time t equals 12 minutes when it started out at t equals 2, being 300 meters east of the origin station, according to these values right here. And then use trapezoidal sums to approximate that value. So in order to find this expression that represents the position function when train A is at 12, we get 300 plus the integral from 2 to 12 of this velocity function. So 300 right here is basically 300 meters east of the origin station while it's still moving east, and then the integral right here represents the displacement change in order to find the final value when train A reaches 12 minutes. And to approximate this integral right here, it tells us to use 3 subintervals and then use trapezoidal formulas to find that, which is right here. The formula is right here, and then as we use the values up here in the charts, we get these three separate subinterval values, and then when we add them all together, we get negative 450 just for this integral. And then after that, we add this negative 450 to 300 to equal negative 150. When it's a negative sign and it says that it's going east, the opposite of east is west. So the final value when train A reaches 12 minutes is 150 meters west of the origin station. And for this 3-point problem, this final value counts as 1. This trapezoidal calculation counts as another. And finally, this expression of train A's position at 12 minutes counts as the final point. Okay, so for the last part of this FRQ, we have a new train called train B that goes north of the origin station away from train A, and it also gives us a velocity function right here. And at time specifically t equals 2, the train is 400 meters north of the station. Find the rate between, or the average rate, the rate of change between the distance of train A and train B at specifically time t equals 2. And as a visual person, I like to draw this out, and I found the Pythagorean theorem and found A from B to be 500 meters apart, and 400 right here of north and 300 east. And with that, I made a Pythagorean theorem equation defining these variables as such, and took the derivative of both sides in order to find the rate of change in the distance between train A and train B. And once we take the derivative, we define these values, the rate of change of train B being 125 after plugging 2 in the velocity equation, and then train A's velocity as 100, and these x and y values with this diagram right here, and z, which is the distance between these two trains, as 500. And once we plug that all in, we find the rate of change between these two trains being 160 meters per minute. For more practices of these type of problems, I've chosen FRQ 2008 Part A and B, which tests the use of slope formulas and trapezoidal sums, as well as FRQ 2010, which also tests the same type of concepts. And where for Part B, where it uses IVT, it's good to go on Khan Academy and search up intermediate value theorem. They have really good practices for that. And lastly, for Part D, we can, since it's testing related rates, we can go back to 3.9 of our calculus book and find a lot of practice there as well.